I'm Roland Minton. These are some of my favorite math stories. In this episode, mathematics is normal. We look at an oddity, a case where one word has several different mathematical meanings. Perhaps ironically, the word is normal. Typically, mathematics carefully defines words and sticks rigorously to those definitions. However, normal can take on different meanings in different contexts, and we will discuss medical research, why being mean can appear to be effective, what makes a genius, and what the ERF function is. We'll start with the concept of a norm. No, not that norm. Suppose we are trying to identify a person on a video by their physical characteristics. We are suspicious that it might be a criminal of known height, weight, and distance between the eyes. Analysis of the video gives estimates of 5 foot 9 inches tall, 170 pounds, and 2.6 inches apart. The criminal's official measurements are 5 foot 8 tall, 174 pounds, and 2.3 inches apart. How close is the video image? Well, you could add the differences, 1 inch, 4 pounds, 0.3 inches, or add the squares of those distances, or take the largest difference. All of these measures of distance are called norms, also called magnitude, distance, modulus, absolute value. The answer you get, how close it is, depends on which norm you use. So careful mathematical analysis identifies the most appropriate norm for the task at hand. You probably noticed how silly it would be to just add 1 and 4 and 0.3 in the above example. The 4 pounds dominates that sum, but 170 pounds versus 174 pounds is not a big difference, whereas 2.3 inches is more than 10% different from 2.6 inches. You should probably normalize the measurements by dividing each value by an average value, say 69 inches, 174 pounds, 2.6 inches, or in some other way put the three errors on the same scale. In what might appear to be a totally unrelated usage, the word normal is used to mean perpendicular, as a normal vector. Now, just to be difficult, we also use the word orthogonal for this purpose. The vector A in this graphic is a normal vector to the blue plane, forming a right angle with the plane. Normal vectors are used to find the fluid flow across the surface, the direction of the lift force on an airplane wing, and many other applications. The mathematician Mark Kotz said there are two types of geniuses, ordinary and magicians. We understand how ordinary geniuses work. They're clearly better at what they do than we are, but we can imagine ourselves becoming that good. The magicians, however, seem to think differently and come up with results that thoroughly mystify us. Kotz said, "They are in the orthogonal complement of where we are." That is, they have another dimension to their thinking that is normal, perpendicular to how we think. Now, let's get to the most common mathematical usage of normal. Suppose that we have some data showing the decreasing sales of a product. To illustrate the trend and predict the future, we can find the line that best fits the data as shown in the graph. That line is called a regression line and is one of the most common uses of mathematics. The theory in this case is that the sales figures truly follow a linear trend, but measurement errors or random fluctuations cause slight deviations from the line. The actual values equal the values from the line plus the errors, which are independent of the year. The two variables, year and error, are normal to each other, like x and y on standard coordinate axes. We will come back to this setting shortly to indicate why the line is called a regression line. An important task in the 1600s was to describe the form of the errors, specifically in astronomical observations, and researchers such as Galileo and de Moivre came up with a symmetric bell curve. In the 1800s, Gauss developed a formula for the bell curve. An early name for the curve, normal distribution, probably came from the errors being normal, perpendicular to the signal. Due to Gauss's work, it is also called a Gaussian distribution. The basic function involved in the formula is e to the negative x squared, which turns out to be an inconvenient function for computing probabilities. There is no simple antiderivative. It is so important for statistics, you use antiderivatives to compute probabilities, that the name ERF, ERF for error function, is given to this difficult function. The term normal distribution was found to be remarkably appropriate due to the central limit theorem, which states that in a wide range of situations, the average of a large number of component parts will have a normal distribution. For example, height is determined by a large number of hereditary and environmental factors, and the height distribution of female humans is close to being normal. Speaking of height, in the late 1800s, Francis Galton collected data for the heights of children and their parents. He found that while tall parents tended to have tall children, they were typically not as tall as their parents. He called this regression to the mean, the trend to regress toward average mean values. The lines that Galton created for parents and children's heights, he then called regression lines, a terminology we still use. Regression to the mean helps explain many phenomena. Why do parents, coaches, bosses, and others sometimes believe that hollering at a poorly performing person helps them improve, while praising a highly performing person causes them to drop off? Regression to the mean would say that someone having an especially poor performance will naturally improve, moving closer to average. Someone with an unusually high performance will tend to drop back towards the average, whether they're praised or hollered at. One of my golfing buddies likes to say after a poor or mediocre shot, "Why can't I hit my normal shot just once?" Of course, all golfers think of their best ever shot when thinking about what is normal for them. Unfortunately for golfers, regression to the best ever is not a thing.